on a few topics which it will be helpful for you for examination. This you can consider as revision for whatever you have studied. So first we have discussed upon the in module 4 we have discussed upon the point sources and arrays, where you have defined a point source. What do you mean by array? The combination of many point sources put together, you can say that it is an array. And you know that you have also discussed about an isotropic antenna, where you can see that efficiency is 100%. And you have also discussed upon various uh, things there. And you also know that pattern, you have discussed about the pattern. Before that, you have seen that the isotropic antenna, it radiates in all the directions 360 degree, and you are having 100% efficiency. So this is what where you feed in the power, and it radiates in all the directions in the point sources. Okay. So next, further continue with, we have also discussed on the power pattern. We have different types of power pattern. We have different types of pattern. We call it as field pattern and power pattern. These are done in order to identify the directivity gain and all those things with respect to the antenna. So here we discussed about the power pattern, and we have also seen the relative power pattern and normalized pattern as well, where you are taking the normalized value. So here further you have divided by its maximum value to get the relative power. So you have taken SR divided by SRM, and all those has been discussed there. Also, you have to find out the power theorem, which we have discussed before. So, in power theorem, we know that the Poynting vector, it's called as the of a sphere of radius r, and the total power radiated by the source is the integral over the surface of the sphere. And we get P is equal to closed integral of S dot ds, and we have written SRds. So here we also found that some of the equations, like the equation for ds is r square sine theta d theta d phi. And we also know that P can be written as SR into closed integral of ds, and when you substitute 4 pi r square, you get SR is equal to P divided by 4 pi r square. So this is what we obtained in case of power theorem. Then we go with radiation intensity. You get U is equal to R square SR, and that is P divided by 4 pi, and we call U as the radiation intensity. And power theorem can be restated in terms of radiation intensity as the total power radiated is given by the integral of the radiation intensity. So we have also come across a few problems where we have discussed about the directivity. And when you write the equation for directivity in terms of Wt, you can write it as 4 pi um divided by Wt. So here we are going to discuss on the unidirectional cosine pattern and the power patterns, in fact. So we are going to discuss upon the unidirectional cosine pattern. Then we are going to discuss upon the bidirectional cosine pattern, and so on. So what we have done in the unidirectional cosine pattern is that we have taken u is equal to m cos theta, and I have discussed with you the important concepts there, that unidirection means the theta value ranges between 0 and pi by 2, and phi ranges between 0 to 2 pi. So you get omega t is equal to Wt is equal to integral of 0 to 2 pi, 0 to pi by 2 u d omega. And when you simplify that, you get it as cos theta is equal to t. And you have to do it in the integration. For that, you take the constant terms outside um, then integral of 0 to 2 pi d phi, integral of 0 to pi by 2 cos theta sin theta d theta. So once you do the integration, you found that you are going to get Wt is equal to You need to substitute for theta is equal to 0 and theta is equal to pi by 2. When theta is equal to 0, you get it as t is equal to 1 and t is equal to 0. So once you simplify that, Wt is equal to pi um you will get. So once you complete it, substitute for directivity, you will get it as 4. And bidirectional cosine pattern, you can also find u is equal to m cos theta. And when you simplify that, you will get Wt is equal to integral of 0 to 2 pi 0 to pi u du omega. And when you do that simplification, you get it as uh, you have to take here one thing you have to understand here is it is bidirectional. When bidirectional, theta will range from 0 to pi, and you have taken cosine pattern, so u is equal to m cos theta. So once you do that, you will get it as integral of um and integral of 0 to 2 pi d phi and integral of 0 to pi cos theta sin theta d theta. So now let me just talk further about integration of this. Integration of 0 to pi cos theta d sin theta d theta can also be represented as 2 times of, you can just go with the limit change, that is 2 times of integral of 0 to pi by 2 it can be. So when you can convert it into 0 to pi by 2 and 2 times of 0 to pi by 2 cos theta sin theta d theta. So when you simplify that 0 to pi by 2 cos theta sin theta d theta, you will get it as 1 by 2. And uh, and when you simplify that, you will get 2 pi um you will get. So directivity is equal to, when you substitute Wt, you will get it as 4 pi um divided by 2 pi um, you will get it as 2. So all these problems has to be, all these things has to be done. Anything can be asked in the examination. So unidirectional sign pattern. So when you do the unidirectional sign pattern, you can just try it out for u is equal to um sin theta. So you can just go through that. Okay, fine. So we can see that in unidirectional sign pattern, u is equal to m cosine theta, and the limits are 0 to pi by 2 and 0 to 2 pi. So unidirectional, you have to do the integration for that, and when you come across the integration, you'll get 0 to 2 pi d phi and 0 to pi by 2 sin theta d theta d theta. So you know that sin square theta d theta can be integrated by taking sin square as 1 minus cos 2 theta divided by 2. So all these things we have carried out in the class. You have to do the solution for that. So when you do the integration of 0 to pi by 2 1 minus cos 2 theta divided by 2 d theta, you will get it as theta minus sin 2 theta divided by 2, and you have to apply the limits. Finally, when you solve it, you end up with the answer pi square um divided by 2. Substitute for the directivity. So directivity is 4 pi um divided by Wt. You can substitute it. So you'll get the final answer to be 2.54. So similarly, you can also do for bidirectional sign pattern. So in the bidirectional sign pattern, u is equal to um sin theta, and you can do the integration for that. So when you carry out the integration for that, you will get Wt is equal to pi square um, and directivity you will get it as 1.27. So for bidirectional sine squared pattern, also you can go with the substitution of u is equal to um sine square theta, and you need to take sine cube theta d theta integration from 0 to pi. So Wt can be written as um 0 to 2 pi d phi and 0 to pi sine cube theta d theta. So you have to use the trigonometric relationship, that is sine cube integration you need to do. So sine 3 theta can be written as 3 sine theta minus 4 sine cube theta. So you can just try these things out. When you solve it for sine cube theta, you have already done the integration for sine cube. You can just check it out for a minute how this can be integrated further. So here, when you integrate for sine cube theta, you can write it as 3 sine theta minus sine 3 theta divided by 4. And when you take the integration for that for sine cube theta for the limit 0 to pi, see all these things we had done at that when the classes were going on, just for you to revise these things. So when you do the integration of sine cube, you get it as 4 by 3. So once you complete it, WT will end up with the answer 8 pi UM divided by 3, and when you substitute for directivity, that is 4 pi UM divided by WT, you will get answer as 1.5. Similarly, you can also do for unidirectional cosine squared pattern, where U is equal to UM cos square theta. So when you are taking U is equal to UM cos square theta, you can see that the WT can be found here by substituting for the limit 0 to 2 UM 0 to 2 pi d phi. So you can get it as 0 to 2 pi d phi as 2 pi, and then you have to substitute for the limit 0 to pi by 2 cos square theta sin theta d theta. So when you are doing the integration for that, you need to take t is equal to cos theta, and dt will be minus sin theta d theta. So after substitution and simplification, you will get as 2 pi um divided by 3. So the directivity will be 6. Similarly, you can also do for cosine squared pattern, where u is equal to um cos square theta, and when you simplify that, you have to take t is equal to cos theta, so dt will be minus sin theta d theta. After simplification, you get it as 4 pi um divided by 3. So after substitution for directivity, the answer will be 3. So similarly, you can do any combinations of sine and cos or tan. So this can be asked for the to obtain the directivity of the problem. So u is equal to, let me take um sine square theta sine cube phi for the limit 0 to pi and 0 to phi also 0 to pi, theta also 0 to pi. So when you integrate for that, you have to do the integration for 0 to pi, 0 to pi, um sine square theta sine cube theta d omega will be substituted as sine theta d theta d phi. So it will be sine cube theta sine cube phi. So already we have done the integration for sine cube. So it will be 4 by 3, and when you substitute that, you will get 16 by 9 and after substitution for directivity, you will end up with the answer 7.07 or 9 pi by 4. So this is what you have found the directivity of various problems, and then to move on further, you have the field pattern. So as you know that any antenna, you can have two patterns, that is power pattern and field pattern. So when you understand about the field pattern, you can say that the point sources has electric field and magnetic field, and this EH plane. EH of both entirely transverse and the wave directions perpendicular to each other. So E divided by H, you can say that the ratio of E by H is Z, and it's a known value that it is 377 ohms. So the E theta and H phi, E phi can be considered as the transverse electric field here. And when you write the equation for SR, that is you will get it as pointing vector. You can say that the conditions of characterizing the field can be pointing vector radial as well as the electric field is transverse. So SR can be written as 1 by 2 E square divided by Z. So you can write also the equations for E, and Z naught is the intrinsic impedance. So all these things is what we discussed before, and moving on further with the very important concept of array of two isotropic point sources. So we can say that the array of 2 point sources. So we are going to see 5 cases here. So two isotropic point sources of same amplitude and phase. You can also have same amplitude and opposite phase. You can also have a third case of same amplitude and quadrature phase. So general case, all these things are the different cases which we have discussed in the previous classes in when we are discussing in module 4. And so first let me take the two isotropic point sources of same amplitude and phase. So you need to understand that when it is same amplitude and phase, and you are considering here 2 point sources. So let me take point source 1 and point source 2, and they are separated by a distance of d. So the d is the distance between the sources 1 and 2, and if you consider from the center, you can say that they are separated by a distance of d by 2. So the distance from the center is d by 2, and separation between the sources is d. So what you can understand here is the distinct point in the direction of phi. The field from source 1 is retarded by, so as I have told you, there are source 1 and 2. So the first source, the source 1 is retarded by 1 by 2 dr cos phi, and the other source is advanced by 1 by 2 dr cos phi. So what is the equation for dr? So dr is the distance between the source and in radians, and it can be also calculated by using the equation 2 pi d by lambda. So dr can be calculated as 2 pi d by lambda, and it is beta d. You will be having all these things for your internals for third IA. So where you have to study from whatever we have stopped in the second IA. From there on, all the topics will be there. So total phase difference is psi. Psi can be calculated as dr cos phi plus delta, and delta here, because you can see that we are doing the case where same amplitude and same phase, or equal phase you can call it as. So when you are going with same phase or equal phase, you can say that delta, the phase difference, will be 0. So let me substitute delta is equal to 0, and when you substitute for delta is equal to 0, you can just see that the equation for psi converts as dr cos phi. So once you get dr as beta is 2 pi by lambda beta d, and psi is equal to dr cos phi. So this is what you get it, and once you get these equations, you can further simplify that to get the equation for the final two sources of same amplitude and phase. So when we go ahead solving it, you get the equation for E is equal to E naught t to the power of j psi by 2, and E naught t to the power of plus j psi by 2. So psi is dr cos phi, and E is equal to 2 E naught e to the power of j psi by 2 plus e to the power of minus j psi by 2 divided by 2. So the entire thing, e to the power of j psi by 2 plus e to the power of minus j psi by 2, you can call it as cos of psi by 2. So you will get it as E is equal to 2 E naught cos of psi by 2, and 2 E naught is the magnitude, and the cos of dr by 2 cos phi is the phase of that. So you can substitute that the distance between the two sources, we can take it as lambda by 2. When you substitute that, you will get dr is equal to pi, and the further simplification, you will get it as E is equal to cos of pi by 2 cos phi, and by using this equation you can simplify that. So this is some of the things which you have to understand this table. This will be helpful for you to plot the graph for this equation E is equal to cos of pi by 2 cos phi. So when you do that, maximum value you can take it as so you have to use, if the function is in terms of cost, you need to use this equations for maximum, minimum and half power, and if it is in terms of sine, you should use this. So you can see that the equation is E is equal to cos of pi by 2 cos phi. So for the maximum, you need to use this equation, x is equal to plus or minus k pi. So when I use that and simplify that, cos of phi maximum will be equal to 0. From this, phi maximum can be written as 90 and 270. From that, what you can understand is the maximum power, maximum is obtained at the values of 90 and 270. So continuing that, similarly you need to do for minimum. E is equal to E cos of pi by 2 cos phi. You have to take it as plus or minus 2k plus 1 pi by 2, which you have already seen that minimum means x is equal to plus or minus 2k plus 1 pi by 2. So from this you have to take it and simplify that phi minimum, you will get it as 0, 360 and 180 degrees. So at these values you have the minimum point. Also, you need to do the half power. To find out the half power, you have to go for the equation pi by 2 cos phi half power is equal to plus or minus 2k plus 1 pi by 4. And you do the simplification, you get the values at plus 60, minus 60 and plus or minus 120 degree. So this needs to be plotted on array axis. So we have to first mark the axis, that is 0, 180 degree, 90 and 270. After that, whatever maximum value you got, it is in 90 and 270, put the points there in maximum. Minimum value you got in 360 and or 0 degree and 180 degree, put the minimum value there. And half power should be drawn slightly down, so you get that 60, 120, 240 and 300. So you can plot it in this way. So what you get here is the entire plot. This plot is called as a broadside system. So you call it as a broadside system. So similarly, now you can just think of going with two isotropic point sources of same amplitude but opposite phase. When you are going with opposite phase, write the equation for that. It is E naught e to the power of plus j psi by 2 minus E naught e to the power of minus j psi by 2. And the simplification of that, you will get it as 2j E naught sine psi by 2, and psi is equal to dr cos phi. So here we are going to discuss on same amplitude but opposite phase. So when you are going with opposite phase, you will get the final equation as 2j E naught sine dr cos phi divided by 2. So this equation is in terms of sine. So you need to use those cases there and simplify that. So when you go ahead with further simplification, you can take 2j E naught as 1 and you can simplify that. So you'll get sine of dr by 2 cos phi. So this equation is in terms of sine, so you have to go with the maximum, minimum and half power points. So let me just take you through the equation. E is equal to sine of pi by 2 cos phi. So here first we have to find out the minimum, maximum and half power. So let us go with the maximum values. So E is equal to sine of pi by 2 cos phi. Finding out the maximum value, you get it as phi maximum is 0 and 180 degree. It indicates that at 0 and 180 you have to plot the maximum points. Then you have to go with half power. Half power you have to take minimum and half power. So let me go with minimum. Pi by 2 cos phi minimum is plus or minus k pi. When you simplify that, phi minimum you will get it as plus or minus 90. If you go with the half power, pi by 2 cos phi half power, you get it as plus or minus 2k plus 1 pi by 4, and half power points will be obtained at plus or minus 60 and plus or minus 120. So this has to be plotted. So plot the array axis and all these angles of 90, 120, 240 and all these lines. After plotting these angles, you need to put the point. So where is the maximum value? You can see the maximum value at 0 and 180 degrees. So at 0 and 180, put the maximum points. So at 0 and 180 we'll be putting the maximum points, and at 90 you have to put it as minimum. So 90 you will be having the minimum value, and 60 you have half power points, and 120 minus 60 plus 60, and minus 120 plus minus 120. So all these points you can put the half power points, and you need to connect it with free hands. So you get this pattern. It is called as the end fire array. So we have studied already the case 1 and case 2, where two isotropic points of same amplitude and same phase, same amplitude and opposite phase. Now the third case is same amplitude and in phase quadrature. In phase quadrature means we have to take pi by 4. So you'll get E is equal to E naught e to the power of j psi by 2 plus pi by 4 plus E naught e to the power of minus j psi by 2 minus plus pi by 4. This is what the equation you are going to get. Here also you need to simplify this further. So when you simplify that, you will get it as 2 E naught cos of pi by 2 plus pi by 4. So it can be, you know, that psi is equal to dr cos phi. When we substitute for psi dr cos phi, you get the answer E is equal to 2 E naught cos of dr by 2 cos phi plus pi by 4. So let us consider that it's a normalized pattern, and 2 E naught is equal to 1. So then you substitute 2 E naught is equal to 1, and D is considered as lambda by 2. So the distance between the two isotropic point sources is lambda by 2. When I take it as lambda by 2 after substitution for dr, you get it as 2 pi d by lambda, or when you substitute that, you will get it as pi. So E is equal to cos of pi by 2 cos phi plus pi by 4 is the final equation what you end up with. And now you have to do the maximum, minimum and half power points. To find out the maximum point, you need to equate it for pi by 2 cos phi maximum plus pi by 4 is equal to plus or minus k pi. And after simplification, you get it as phi maximum is equal to cos inverse of 1 by 2 minus 1 by 2, and phi max will be 120 and 240. Minimum values also you get it as 60 degree, and half power points you get it as 180 degree. So this now you have to plot it in the graph. So you can say that the minimum value is at 180 and 0, and the maximum value got it as 120 and 240. Then you get the half power values at 180 degree. So here you get the minimum you got it as at 60 degree is minimum, then maximum is 120 to 40, and half power is 180. So you can see that the half power point has to be drawn slightly inside. So once you do that, you have to connect all the points. You get the pattern in this form. So this is when two isotropic point sources of same amplitude and in phase quadrature. Okay, so that is what you get it here. Once you complete this, now next is case 4, or you call it as a general case of two isotropic point sources of equal amplitude and any phase. So you can consider any of the phase. So when you take any of the phase, you can say that it can cover up the case 1, 2 and 3. So it will be easy to understand that if you come across case 4, it will cover all the 3 cases 1, 2, 3. Okay. So we will discuss upon a general case of two isotropic point sources of same amplitude and any phase. So when I am considering any phase, you can say that the equal amplitude but of phase difference is delta we are taking here. So psi will be dr cos phi plus delta. So when I move on further, E is equal to E naught e to the power of j psi by 2 plus E naught e to the power of minus j psi by 2. Simplification of these things, you will get it as 2 E naught cos of psi by 2. So D will be lambda by 2. Substitution of D, dr will be equal to pi. So E is equal to cos pi by 2 is what you finally, cos of psi by 2 is what you get it. Substitution of psi is what, psi is already written, psi is dr cos pi plus delta. So let me just substitute that in place of psi as dr cos pi plus delta. Dr is pi, so pi by 2, so I'll get it as E is equal to cos of pi by 2 cos pi plus delta by 2. So as I have told you, this is a general case where you can say that the case 1, 2 and 3 all can be covered within this case. So I can say that it is a special case when delta is equal to 0, delta 180 and delta 90, you can say that you will get case 1, 2 and 3. So the last case is case 5, the most general case where the two isotropic point sources of unequal amplitude and any phase difference is considered. So here the two isotropic point source exists when the amplitudes are unequal and the phase difference is arbitrary and has a large amplitude E naught. So two sources we can say of different amplitudes. So in fact, so one is E naught, another is A E naught, and the distance between distances R as shown in figure. So this is what the figure we have drawn at that point of time to explain it. So we got the equations for that for any amplitude and any phase. Okay, so we can write it as E is equal to, so finally when you end up with this, you will get it as E is equal to E naught root of 1 plus A cos pi whole square, cos psi whole square, plus a square sin square psi angle tan inverse of this. So where psi is equal to dr cos pi plus delta. This is was the most general case equation which you will get. Then also we have discussed upon the non-isotropic but similar point sources with the pattern multiplication, where you have seen that you can understand what do you mean by a pattern multiplication, where you are taking combinations of two. So in the principle of pattern multiplication, you can say that the total field pattern of an array of non-isotropic but similar sources, the product of individual source patterns has to be considered. So when you go for the pattern multiplication, you have to take the multiplication of the field pattern as well as the combination of the phase pattern. So here the individual sources are having the same relative amplitude and phase, while the total phase pattern is the sum of the phase pattern of the individual sources. So E is equal to f of theta phi, capital F of theta phi, and angle of f of fp of theta phi and plus capital Fp of theta phi. So what you can see here is f of theta phi is the field pattern of individual source, Fp of theta phi is the phase pattern of individual source, and capital F of theta phi is the field pattern of array of isotropic sources, and capital Fp of theta phi is the phase pattern of array of isotropic sources. So let me consider the find the total field pattern of two isotropic point sources having distance d is equal to lambda by 2 from each other, and each source field patterns is given by E naught is equal to E naught dash sin phi, and assuming delta is equal to 0, so we can say that E is equal to 2 E naught cos of psi by 2, and psi is equal to dr cos pi plus delta. So dr is pi what you obtain, and E is equal to 2 E naught cos of pi by 2 cos pi. So when you simplify that, you will get the pattern in this form. So you'll get the pattern in this form, the pattern of first and the pattern of second. So what you get here is the equation is E is equal to sin phi cos of pi by 2 cos phi. So what you can see here is sin phi, you'll get one pattern, and cos of pi by 2 cos phi, you'll get another pattern. So when you do the multiplication of these two patterns, you can say that you'll get the final pattern in this form. So it will slightly narrow down, that is what you get. And similarly, if you go for E naught is equal to E naught dash cos phi, and when you take simplification of that, you will get cos phi into cos of pi by 2 cos phi. Let me draw the patterns for both. So let us see that the cos phi pattern for cos phi will be in this direction. The maximum will come into 0 and 180 degree, and minimum will be 90 degree or 270 degree. But when you go with the other one, that is cos of pi by 2 cos phi, you'll get maximum in 90 and 270, minimum in 0 and 180 degree. So let us multiply these two things. So you will be getting the pattern in all the four directions. So you can say that this is what you will get in all the four directions. You will get the pattern in all the four directions. So cos pi, cos of pi by 2 cos pi you will get. So the pattern will be in the all the four directions. Because of atmospheric noise, when the two field patterns of the antenna will overlap each other, then you will get the pattern in this form. Next, we have to discuss upon the linear array of isotropic array of n isotropic point sources. So here, linear array of n isotropic point sources of equal amplitude and spacing, where you can see that we have taken not one isotropic source or two isotropic source, we are taking n isotropic sources. So n isotropic sources are placed at a distance of d, which is separated by each other. So you can see that the source 1 and source 2 is separated by d, source 2 and source 3 is separated by d. So each source is separated by a distance of d. So this from here on we will revise it for the next class, where we will be discussing on linear array of n isotropic point sources of equal amplitude and spacing. So from here on we will discuss in the next class. So if you have any doubts or anything till here with respect to any of the concepts, you can discuss with me now. So I will wind up here today, and we will continue with the revision in the upcoming classes. Okay. So as you know that the entire syllabus is completed, so for your better prospects, I thought I will just go through this module 4 and module 5 once again for you. Okay. So if you have any doubts, you can discuss. Otherwise, we will wind up for today, and we'll get back. I'll get back to you in the next class. Is that clear for all of you? Okay, fine. Okay, fine. We'll stop it for today, and thank you. We'll meet in the next class. Thank you.